So this is the session on synchronous generators. We will start with the construction and operation of the same. Straight away, right, to get started, what you're seeing on the screen, I believe you're seeing it on the screen, is the construction of a synchronous generator. That's a simplified version whereby you have the rotor and you have the stator as well. So this straight away is the cross section. You have your stator as the circle that is there, and in this diagram we are representing the rotor with this two-pole magnet. So the operation of synchronous generators is such that, so what happens is you have a magnet that is placed inside the stator and it is rotated, as you can see, and through the effect of induction, electromagnetic induction as per Faraday's law, you will have essentially an electrical current being induced because of the magnetic field that is being induced. Right. So essentially, that is the mode of operation of the synchronous generator. So as you've seen from the animation, which I will share the video, the rotor is a magnet that is placed inside the stator and it is free to rotate. So we call the rotor the field windings because it is supplied, as you had seen from the animation, with a DC field, and that produces a magnet with two poles, or in the case of that animation, 4 poles, right? So the field is in the rotor, and the stator now contains the armature windings, right? So you would take off the power, which are these windings here, in the form of 3-phase. You would have 3 stator windings that are 120 degrees apart from each other. And the field is supplied from a DC source that you have externally to the machine itself. It is usually supplied through slip rings, but we will see some certain variations in the same. So what you see on the machine is you have a 3-phase supply that is, as we have gotten used to, throughout all sorts of mains or 3-phase. It is just a normal 3-phase supply, bearing in mind the fact that the windings have been placed 120 degrees apart from each other. Okay, so you would find that generally the windings have a short cylindrical base, and you would have salient poles. That is, they are not a cylindrical rotor, it is salient poles. Each of these represents a pole that is providing magnetic field to the machine, right? And what you see here now, this is the exciter, that is the field windings that are supplied to the machine. Straight away you notice that the windings themselves are very small compared to the rest of the machine. So what you're doing is you're supplying a small current or a small field, and it is able to generate a larger field that is there. Okay, so in some of these cases, what you will end up seeing is you need a different kind of exciter, whereby you would want to have a way in which you avoid having a DC source, because generally in a power plant you would already be having the 3-phase power. If these things are connected parallel to each other, these generators or alternators are connected next to each other, you would probably have AC sources around or nearby. So we are next going to look at the exciter. One of the other things that we've seen is that the frequency of the field supplied will be given by the speed of the mechanical movement times the number of poles over 120. So the frequency itself is only proportional to the speed of the prime mover and to the number of poles. So in the case of a machine like this, you have a large number of poles. You have a large number of poles that are all over the machine itself. That means that such a machine would be able to be rotated at a very slow speed while still being able to create the frequency that we would require, which is of course generally 50 hertz as per the Kenyan standards. So now let's look a bit at the excitation. So field excitation. So what this diagram now represents is the schematic or the circuit diagrams of the field excitation. So on the upper part of the diagram, these sections, you have the rotor. These are all circuits that are mounted on the rotor. And below, you have circuits that are mounted on the stator side. The circuits that are on the rotor rotate with it. So you have the field, the rectifier, the exciter, armature. These all rotate together with the movement of the windings themselves. And you have these, the stator, which are fixed onto the stator, so there is no rotation. They do not move, they are stationary. So you have two of them. You have a field input, and you have the main armature, which is the actual output of the three-phase power that you're talking about. Okay, so the main machine itself is, first of all, this section. This is the main operating part of the machine. You have your field winding, which acts as your magnet that is rotating inside the stator. So through the act of electromagnetic induction, through the principle of electromagnetic induction, that movement of the magnet cutting across the armature windings creates or rather an electrical voltage, and if you connect a load to it, it will also create an electrical current that will flow through the circuits as an output. Okay, now you want your magnet here. So how do you create your magnet? You supply IF, which is a DC current. How do you get a DC current? That is what this circuit is for. So you have a rectifier connected to a small three-phase circuit which has an AC current. Okay, on this side it is AC, it is rectified, it becomes a DC that flows as IF. This is the field current that flows through the field windings and will be able to give you an interaction with the armature windings so that you have an output. So these windings, if we relate it to the photo that we've seen on this side, these windings are now the ones that are here. So these are the field windings, and the exciter here, the rest of this circuit that you're seeing on this part, right? So the main field windings are the many poles that you saw in the diagram, and the exciter is mounted on the same shaft as the rotor. So the rectifier and the smaller windings that are supplied are mounted on there. Now, at the same time, how do you get your AC current onto the rotor itself? You have a number of options. You can have, on the stator side, you have a three-phase current that in turn magnetizes another exciter field that passes on to the armature through either through transformer action, right? So you have your DC here, but because it is interacting with windings that are mounted on a rotor and that are rotating, you have this one inducing a current in this field. Okay, so there's an interaction between the exciter field and the exciter armature, and then the exciter armature is rectified to give you the main field. So it is a sequence of input of three-phase AC rectified to DC again, or for the first time. DC induces an AC within the armature. So you're going from DC to AC through transformer action. Then AC is rectified back. It becomes the main field winding or main field current. And then that in turn interacts with the main armature. Okay, then you have your output on that side, right? If you want to make them fully independent, because you still have, you would have a three-phase input that you're putting into your entire machine. If you want it to be fully independent, that is to be self-starting, you can add an extra element whereby you have this section called the pilot exciter that you add to your exciter field, right? So instead of your exciter field being connected to three-phase power, you could have small permanent magnets, which in turn, so you have like the action of a generator here, creating a three-phase AC, then it is a DC, then it becomes through transformer action, another AC here, then DC, and back again to your main armature, and finally you have your full output. Okay, so in that way, it is almost like amplifying. You're building up your currents and your voltages so that they in turn create an output as you require. Remember, the rotor it is always in motion. Yeah, it is always rotating. And the stator is always stationary. So the interaction between these parts is what now indicates or gives you your operation of motor or operation of a generator. Any questions so far?
Yes.
Okay. Excuse me, I have a question.
Yes.
What's the reason for having the permanent magnet for the pilot exciter field and not just have it at the exciter field?
It is kind of like amplifying. Generally, you would not have magnets that are powerful enough to provide a current that is needed. So it's almost as if it is like a two-stage generator, if I can call it that. Yeah. So each stage builds onto the next stage. Get it? So at the first stage, at this stage here where you have your permanent magnets, the permanent magnets, by their action with interaction with the exciter armature, can generate a small current that is then pushed through. And at each stage, because you're inputting the rotating energy, at each interaction between, let me use a different, at each interaction between, every time you're crossing between stationary and rotational, you are adding, almost like you're adding the energy input of the rotation of the prime mover into that, and that becomes your amplifier. You're converting the rotational motion into electrical energy. Okay?
Okay. Thank you.
Now, so when you have your field that is rotating inside the armature, it generates an electrical voltage. So how does that relate to the principles or the construction of the machine? So what you will find is you have an internal generated voltage, which is what we had, let's go back here, which is what we have here. This in the, not in the armature, sorry. Yeah, in the armature, you have an internal voltage that is generated. This output that I'm talking about is actually a voltage called terminal voltage, right? That is your useful voltage that you can actually take off, and you can have a current in the armature that you can now make use of outside of the alternator. However, within the armature itself, when you have your conversion from rotational mechanical energy through the action of the induction, Faraday's induction principle, you have an internal generated voltage, which we call E in the armature, which depends on a number of factors. So it is given by K phi omega. So your internal generated voltage, which is that, depends on, first of all, the flux. Okay, that is the magnetic field that is coming from your field windings, right? So we've talked about here that you have an interaction between the two of them. So this DC current that is flowing here, this field current that is flowing here, creates a magnetic field which has a flux called phi. Yeah, it is called phi. So that magnetic field that is here, the magnitude of that field determines the amount of, or the magnitude of, the voltage that you will get. It is dependent on flux or magnetic field. At the same time, it is also dependent on the speed. We talked of what is the speed of rotation, and that one is what determines your energy that passes across, or rather your voltage that is put across. So the speed of rotation via the prime mover, which we indicated previously, it's related to the frequency, which depends on also the number of poles that you have and the speed of rotation of the actual prime mover. And the final factor that we would need to look at is here what we are calling K. So these are construction factors. These are a number of them. So now that these ones are a way of indicating the construction of the generator that we have. So like in the photo that I showed, you have a large diameter armature field winding which has a short length. Yeah, if you had a longer length and maybe a smaller diameter, that one has a different impact on the way the internal generated voltage or the magnitude of the internal generated voltage that you have. So some of these construction factors are the pitch. When we talk of pitch, is how far apart are the windings? What is the step from one winding to the next? What is the distance in between? You also have KB, which is distribution, a distribution factor. How closely packed are these windings? You know, are they, what is the nature of their distribution along the surface of the rotor? And then you also have KF, which is the form factor of the windings. Are they square? Are they round? What is the shape of the coils that are there? And finally, you can also have T, which is the number of coils that you have, right? So these are now the main determining factors that will let us know what is the magnitude of the internal generated voltage. By far, the biggest factors are this flux and the speed of rotation. The construction factors tend to alter, I can say, the shape of the waveform, yeah, how regular or irregular it is. But generally, the biggest factors are the magnetic field, and the magnetic field, once again, is determined by the field current, IF, right? So that is a direct way in which you can alter the generated voltage, right? And because of this, you can have a characteristic whereby if you compare the magnitude of the flux and the magnitude of the field winding, the relationship between the two is generally linear up until the point you get saturation, of course, right? So by and large, if you have the field current being varied, you can alter the magnitude of the flux that is available within the space of the machine, so within the field winding.